Hello everyone, this is Prajwal. In this video, we are going to discuss a topic under cryptography, which is symmetric key distribution using symmetric encryption. The topics in this video are different techniques of key distribution, how to distribute key between two users, different types of keys, key distribution scenario, hierarchical key control, session key lifetime, a transparent key control scheme, decentralized key control. Key distribution. Symmetric key distribution using symmetric encryption. When two parties share the same key, that is symmetric key, that protect from access by others. The process between two parties that exchanges that key called a symmetric key distribution. If two people wants to communicate with each other via messages or exchange data without interference of other, two parties, person A and person B, achieve the key distribution in various ways. A can select a key and physically deliver it to B. A third party can select the key and physically deliver it to A and B. If A and B have previously and recently used a key, one party can transmit the new key to the other, encrypted using the old key. If A and B each has an encrypted connection to a third party C, C can deliver a key on the encrypted links to A and B. Option 1 and 2. Option 1 and 2 calls for manual delivery of a key to the users. Manual delivery of a key is difficult in a wide area distributed system. Returning to our list, option 3 is a possibility of either link encryption or end-to-end encryption. But if an attacker ever succeeds in gaining access to one key, then all subsequent keys will be rebuilt. For end-to-end encryption, some variation on option 4 has been widely adopted. In this scheme, a key distribution center responsible for distributing keys to pairs of users as needed. Each user must share a unique key with the distribution center for purposes of key distribution. Key distribution scenario. The key distribution concept can be deployed in a number of ways. A typical scenario is illustrated in the figure. Okay. Initiator A and responder B. Initiator A will be connected to the key distribution center. The key distribution center provides a key to the initiator A, which will be shared between initiator A and responder B. Between the initiator A and responder B, authentication steps will be performed. The scenario assumes that each user shares a unique master key with the key distribution center. Let us assume that user A wishes to establish a logical connection with B and requires a one-time session key to protect the data transmitted over the connection. User A has a master key, Ka, known only to itself and the KDC. Similarly, user B shares the master key KB with the KDC. Let us discuss all the steps. Step 1. A issues a request to the KDC for a session key to protect a logical connection to B. The message includes the identity of A and B and a unique identifier N1 for this transaction, which we refer to as a nonsense. The nonce may be a timestamp, a counter, or a random number. The minimum requirement is that it differs with each request. Also, to prevent masquerade, it should be difficult for an opponent to guess the nonce. Thus, a random number is a good choice for a N1s. Step 2. The KDC, Key Distribution Center, responds with a message encrypted using KA. Thus, A is the only one who can successfully read the messages, and A knows that it originated at the KDC. The message includes two items intended for A. The one-time session key, KS, to be used for the session. The original request message, including the N1s, to enable A to match this response with the appropriate request. Thus, A can verify that its original request was not altered before reception by the KDC, and because of the N1s, in addition, the message includes two items intended for B, the one-time session key, KS, to be used for the session, an identifier of A, IDA. These last two items are encrypted with KB, the master key that the KDC shares with B. They are to be sent to B to establish the connection and prove A's identity. Step 3. A stores the session key for use in the upcoming session and forwards to B. The information that originated at the KDC for B, namely E of KB, because this information is encrypted with KB, it is protected from the eavesdropping. B now knows the session key, knows that the other party is A, and knows that the information originated at the KDC because it is encrypted using KB. At this point, a session key has been securely delivered to A and B, and they may begin their protection exchange. Step 4. Using the newly minted session key for encryption, B sends a N1s and 2 to A. Step 5 is also using KS, A responds with f of N2, where f is a function that performs some transformation on N2. Example, adding 1. Symmetric key distribution technique using symmetric encryption. There are 4 different methods are used. Hierarchical key control, session key lifetime, a transparent key control scheme, decentralized key control. Hierarchical key control. It is not necessary to limit the key distribution function to a single KDC. Indeed, for very large network, single KDC is not enough to distribute keys among all users. As an alternative, a hierarchy of KDC can be established. Hierarchical key control. For example, there can be local KDCs, each responsible for a small domain of the overall internetwork, such as a single LAN or a single building. For communication among entities within the same local domain, the local KDC is responsible for key distribution. If 2 entities in different domains desire a shared key, then the corresponding local KDCs can communicate through a global KDC. In this case, any one of the 3 KDCs involved can actually select the key. The hierarchical concept can be extended to 3 or even more layers, depending on the size of the number of users and the geographic scope. Session key lifetime. The more frequently session keys are exchanged, the more secure they are, because the attacker has to capture session key every time to decrypt ciphertext. Short session key lifetime. Key exchange frequently and more secure. Long session key lifetime, reduce key exchange time and less network bandwidth used. For connected-oriented protocols, new session key for each new connection. Update key periodically if the connection has long time. For connectionless protocols, not to use a key for each session, not to use a new key for each session, but use a given session key for a fixed period of time. A transparent key control scheme. The steps involved in establishing a connection are shown in the figure. When one host wants to set up a connection to another host, it transmits a connection request packet. That is step 1. A transparent key control scheme. The session security module saves the packet and applies to the KDC for permission to establish the connection. The communication between the SSM and the KDC is encrypted using a master key, shared only by the SSM and the KDC. If the KDC approves the connection request, it generates the session key and delivers it to the 2 appropriate SSMs using a unique permanent key for each SSM. The requesting SSM can now release the connection request packet, and the connection is set up between the 2 end systems. All user data exchange between the 2 end systems are encrypted by their respective SSMs using the one-time session key. Decentralized key control. Decentralized key control is not practical for larger networks using symmetric encryption only. It may be useful within a local context. A session key may be established with the following sequence of steps. Decentralized key control. A session key can be established using the following steps. Step 1. A issues a request to B for a session key and includes a N1. Step 2. B responds with a message that is encrypted using the shared master key. The response includes the session key selected by B, an identifier of B, the value of f of N1, and another N1s, N2. Using the new session key, A returns f of N2 to B. Thank you for watching this video.